In this demonstration, I'm going to show you how we can activate outputs on the PLC without using any contacts or coils in the program, just to illustrate how the bits work in a PLC, the input-output bits, and also to show you another instruction. So right here I have the RS Logix Micro Starter Lite software in the offline mode. I'm going to enter a new rung in my program, and in this new rung I'm going to go to the Move Logical tab on my toolbox. I'm going to bring down a masked move instruction. I'm going to place it here. There's no contact in this rung, which means this instruction will always be executed through every scan of the program. It's asking me for a source of data. I'm going to give it an input file, element 0, word 0, so 0.0. Notice I did not use a slash mark. I'm not looking at bits here. I'm looking at whole words. And click OK. It's asking me for a mask. When it reads this word, it wants to know which bits in that word I want to move to the destination. In this particular case, the word I entered in for the source is the word corresponding to the discrete inputs on this PLC. This is a MicroLogix 1000, the smallest PLC they make. This particular model of MicroLogix 1000 only has 6 input bits. I'm only going to be using the first 4 as I want to move them to the destination, which is going to be the output word. To turn on those 4 bits. So I'm really interested in the last 4 bits, the least significant 4 bits of the input word. So what I'm going to do is enter a hexadecimal number that masks or selects which bits of my source word I'm going to move to my destination. Since I'm interested in the last 4 bits of my source word, I want the last character of my hexadecimal number to be the letter F. It's going to be 000F, and I'll end it with the letter H to let them know it's hexadecimal, and there we go. So if I were to expand that into binary form, that'd be 0000, 0000, 0000, 1111. The last 4, the least significant 4 bits of that 16-bit mask is going to select the least significant 4 bits of the input word I0.0. Now for destination, I want to move these bits to the output. So O, colon, element 0, word 0, 0.0. There we go. I won't bother to put a symbolic name in there. And thus concludes my masked move instruction. It's going to read the input word here, and it's going to copy or move the last 4 bits of that input word to the last 4 bits of my destination word, which in this case is the output. What this means is I've basically coupled the least significant 4 bits of my input to the least significant 4 bits of the output. So when I turn on my first switch, my discrete input switch for bit 0, it should turn on bit 0 of my output, my destination. At this point, my program is concluded, so I'm going to save this. I'm going to download to the PLC. And yes, I want to download. I want to switch out of run mode. It's now downloading the information. Change back to run mode, and I will go online so I can see what's happening. Now looking at my PLC, as you've seen before, I have a series of input switches, 6 of them, tied to 6 discrete inputs on the PLC. The 4 discrete outputs, the status of them can be seen by these LEDs. If I turn on the first switch, you notice the first LED comes on for the input, and correspondingly so does the first LED for the output. I'll continue to turn on the first 4 switches, and there we see 4 input lights lit up, 4 output lights lit up. Bit for bit, all this program is doing is transferring the least significant 4 bits of the input to the least significant 4 bits of the output word. Let's take a look now at the program and see how it reads. Focusing on the masked move instruction, it shows me the live values of the source word and the destination word. So if I turn on the least significant bit, input 0, the source, it shows up as a number 1, because that is the decimal value of that 16-bit word with the least significant bit on, 1, and all the others 0. If I turn that off and go to the next input switch, I see a 2. If I turn that one off, go to the next input switch, I see a 4. If I turn that one on, go to the next input switch, I see an 8. So it's counting in a binary sequence as I go up 1 bit at a time in my input. If I turn all 4 input switches on, I see 15, which is the decimal equivalent of 1111. And you can see whatever number appears here also appears down here. So as I turn these switches on and off in various patterns, you see here whatever number, whatever value appears in my source gets moved to my destination. So once again, what we're doing is we're looking at a series of bits on the input, the first 4 in particular. They're being moved over to the 4 bits of the output. I'm turning these on in whatever sequence I wish, on and off. I see a direct correspondence between those 4 input bits and those 4 output bits. There's one more way we can view this, and that's if we go over here to the data files and I pull up a view of the input word, and if I also pull up a view of the output word. If I look at both of those, we see in binary format the 1s and 0 statuses of the first 4 bits input and output. Right now I have bit 2 and 3 energized on the input. We see bits 2 and 3 set to a 1 value on the output. As I turn these switches on and off, you see direct correspondence between input word and output word, because the mask move instruction is directly taking those first 4 bits and moving them to the first 4 bits of the output. So turning these on and off in random order, you see once again direct correspondence. So I wanted to show you this program to demonstrate to you how you can turn output bits on and off without using any contacts or coils in the program itself. Simply a move instruction moving those bits over. I want you to clearly understand the relationship between the bits, the input, output of the PLC, and the words that you see in the data files. And later on you'll understand how those bits are going to correspond to the contact and coil instructions, contacts being reading the bits and coils being writing those bits. That's what we're looking at here with a PLC.